Okay, so we're now starting calculus finally into the limits and continuity section of this course. Before you begin, please download either the Word or the PDF document so that you have a hard copy of these notes and print them out. Make sure you have them printed out so that you can copy these down, and then we'll be good to go. So before we begin our lesson today, can you just copy what I have already down? You can press pause so that we can begin. Okay, so limits and continuity. First, we're going to look at the definition of the limit. This is read as the limit of f of x as x approaches a is L. So that's how you kind of read that. It'll make more sense when we actually look at this graphically. So here I have an x squared graph. And in this example, we are looking for the limit of f of x, which is x squared, as x approaches 2. So we're going to look at x equals 2 and see what y value it seems to take on in our graph. And by the looks of it, it's going to be 4. So in this graph, it's pretty easy to read off of. However, if you look at example 2, it's a bit more difficult when you have discontinuities and holes in it. And we're just going to look at each example case by case to get an idea of how this would work out. When you're looking at limits, you're actually looking at not when x is equal to 2, as in this example, but we're looking at what happens when x is really, really close to 2. So even if you have holes, you can still find the limits because all we care about is how close we are to that y value. So let's look at the first one, the limit of f of x as x approaches -5. Looks like we're approaching y equals 0 here, so your overall limit's going to be 0. I'm going to write this in a different colored pen so you can see the answer. Then for the next one, we're going to approach -4. So -4 is over here, that's your x value. We're going to look at our f of x. So as we approach x equals -4, it looks like our y value is going to be at 5. The next one, the limit of f of x as x approaches -2 from the left-hand side. This negative means we're going to approach it from the left-hand side. And this positive means we're going to approach it from the right-hand side. So from the left-hand side, as I'm approaching x equals -2, it looks like our y value will be 8. And then from the right-hand side, it's going to be different. If you just look at my cursor, it looks like it's going to approach 5. Now, if we look at the overall limit of f of x as x approaches -2, there's two different values here. We can't say one or the other. And when there is no certain one value, we just say they do not exist. A D and E do not exist. Because if you look at our picture, it looks like there's more than one value. And we only can have one value. F of -2. So this is the actual value that this function will take on at x equals -2, and that's going to be 8 because we have a closed circle here. Now moving on, limit of f of x as x approaches 3 from the left-hand side. So as we approach x equals 3 from the left-hand side, our y value looks like it's going to be -7. And then approaching it from the other side here, from the right-hand side, looks like we're going to be at 5. However, if you look at f of 3, the actual value this function takes on is going to be at this point here, this actual point, which is part of the domain, and it's at 1. Lastly, again, because if you look at our overall limit, it doesn't really tend to a specific number, so it's just going to be D and E. Now let's do another example, but before we do that, we should probably link what we just talked about this here, about these D and E limits. The reason why these limits don't exist is because the left-hand limits and the right-hand limits are not the same. We have a -7 and 5, so then your overall limit does not exist. That's what it's saying here. The right-hand and left-hand limits must be the same for the limit to exist. Okay. This is a very important theorem to know because we'll be using this a lot in this unit for sure. So both sides of your limit have to exist and be the same for the overall limit to exist. Okay, this next example says we need a graph using graphing technology. You should have a TI 83 or 84 for this course because you're going to need it for the final exam if you do decide to do the AP Calculus exam from the College Board. So these are calculators that run from $70 to $90. I know it's an expensive investment, but it's going to be very helpful for you for graphing. Now, I'm just going to use Desmos, and you can use Desmos in the meantime if you don't have a graphing calculator. And I've already put this graph up on Desmos right here. So this is a graph that we are looking at. Now, we're trying to approach this graph at x equals 2. But if you put your cursor over here and find 2, it's going to say undefined. So that means we have a hole in the graph. Now, if we approach 2, but slightly smaller than 2, look at our y value. It's 4.04. And if we look from the other side, maybe 2.0 something, we get 3.9. So it looks like as we get closer and closer to 2, we're gonna maybe hit around 4. So that would be our limit. Now we're gonna record this down here. So I'm just gonna quickly draw a sketch of this graph. And again, we only care about x equals 2, so I'm only gonna draw the one side. Okay, so if you just think about this side, your left side, when x is equal to 1.999, you're going to get a y value that's 4.0001. If you try to approach it from the other side, the right-hand side, your x value will be 2.0001, and your y value is going to be 3.9998. So it looks like if we get closer and closer to 2, our y value is going to be 4. So the limit as x approaches 2 of x squared plus 4x minus 12 over x squared minus 2x is 4. That's what it looks like on the graph. We can also do this algebraically as well. So this is the direct substitution method for polynomial functions. You just plug that value into your f of x, and then that'll be your limit. But if you look at this question here, which is the same as what we just did, doing this algebraic, if I plugged in a 2 in here, I'm going to get 0 in the denominator. We can't have that. So we had to manipulate this function a little bit first before we can plug it in. I'm going to factor the top and bottom. And then you can see we can cancel something out here. And then we're going to be left with x plus 6 over x. Notice I'm consistent with my limit and the x approaches 2 at the front of the functions because this is your definition of the limit. You have to have that there or else your notation is wrong and then your overall what you're saying is wrong. Okay, so now if we plugged in 2, it looks like it'll be okay. We're not going to get a 0 in the denominator, we're going to get an actual number. So 2 plus 6 over 2 is 8 over 2. So our overall limit is 4, and that matches up with what we had from above. Lastly, we're going to look at the property of limits. So let's just say the limit of f of x as x approaches a is p, and the limit of g of x as x approaches a is q. So if we have f of x times g of x, we can actually split the limit so that we have two limits and they're multiplying by each other. We could also simplify it even further. If we can evaluate this, and that's p and this is q, we can just say that's p times q. The same rule can apply for addition, subtraction, and division. So just take a look at all those. 5, 6, and 7 are a bit different. So 5, we're just saying the constant that's in front of your f of x. We can pull this out to the front. So let's just say it's 5 of x. We can pull it out to the front, so your 5 is at the front of the limit sign. Evaluate the limit. So it could be 5 times whatever your evaluated limit is. So c times p. 6, so we can just pull out the exponents, evaluate the limit itself, and then take that to the power. Lastly, for 7, the limit of any constant is still that constant. So the limit of, let's say, 5 as x approaches 0 is still going to be 5. Now let's apply those properties to 2 different examples here. So if you look at this first one, we have a function times a function. This would be our first property. So I'm just going to rewrite it and apply that property. And then we can evaluate each limit. So the limit of e to the x as x approaches 0, that's the same thing as saying e to the 0 times cos of 0. Then we can evaluate this. E to the 0 is 1, cos of 0 is 1, so your overall limit is 1. For the next one, this would follow from our 6th property. So we're going to take that power out, that cube power, and we're going to evaluate the limit on the inside first before we cube it. So what we're looking for here is cosecant pi over 6 cubed. I'm going to quickly draw a triangle so we can find out what that is. So cosecant, remember that's hypotenuse over opposite. So our hypotenuse is 2, our opposite is 1. So we're going to do 2 cubed, which is 8. So that's our overall limit, and we are done. Okay, so that's all we're going to cover for this lesson today. I've uploaded some worksheets in your homework section in the OneNote. You can do the 2 worksheets. I know there's 3 up there right now, but just do the 2. The first one is one that's on graphing. So find the limits given the graph. And the second worksheet says evaluate the limit by direct substitution. Okay, so those are the 2 worksheets that you can get started on so far for this lesson. For the third worksheet, we're going to do that next lesson.